or you had put up your hand. Eric. Today you won't see me. I have a problem with my camera, but I hope the sound is clear. Today we are going to look at start looking at a new area. Actually, is we are trying to get to how the generator polynomials, generator polynomials are constructed, and we specifically look at a particular case of codes, which are called the BCH codes. And actually, it's not just BCH, because all these codes are somehow related. You'll find that some of the codes we are looking at, like Hamming codes, they are special case of BCH codes. And actually, finite fields work with all cyclic codes, and you find most of the codes we have been dealing with are actually cyclic. Now they are mostly cyclic. They are linear. Yeah. Actually, linear is one of the requirements. So we are going to look at the background, or rather various knowledge areas you need to have to do construction of cyclic codes, and specifically the BCH codes and Reed-Solomon codes. So, what are cyclic codes? Cyclic codes are just codes in which a circular shift of a valid code word is a valid code word. And in this case, when we talk about valid code word, we are saying a code word that was generated by a specific generator polynomial or generator matrix. Because sometimes you can be using a polynomial, or you can be using a matrix. But it means if it is a valid code word, then it means it was generated by validity refers to a particular generator matrix or generator polynomial. You remember the example we were working with? We are working with the 7-4 linear, block code, linear systematic block code. I hope you are still familiar with those terminologies, linear and systematic. It is systematic in that the message, it has two distinct parts, the message and the error checking bits. So the K message bits and N-K error checking bits. And obviously you can see why this is very important, because it is easy to decode. Yeah? Because this is very easy to decode, because if it is systematic, you can simply check whether this code word is valid, and Joraki, you can tell us how we check whether a code word of a linear block code is valid. How do you do it? How do you do that? How do you check that? You have received the code word at the receiver, and you want to establish that it is valid. Yoraki, John. Or anybody, can anybody tell us that? Can anybody assist in that? Yes, Samuel.
Yeah, I can attempt.
Yeah.
Yeah, we earlier looked at syndrome decoding, where if we get the syndrome to be 0, it's a valid code word.
Yeah, you're right. What you do is you get the syndrome, which is simply multiplying the received vector with the parity check matrix. And if you get a 0, it means that is a valid code word. It may not mean it's a correct code word, because correct is only correct because to get a valid incorrect code word, it means you need to change at least 3 bits. It means the errors have to be so bad that they have flipped 3 bits, because 3 bits is the minimum distance of that code. So you'd have to change 3 bits at a minimum to get another code word that is valid, because this system does not check a correct code word. It just checks that that code word is valid, or rather it is one of the 16 that were derived from the 16 4-bit message vectors. Yeah. So that was so the course we are dealing with our linear block code, and what we are going to look at mainly, the ones which can be generated with this method, are the cyclic codes, because cyclic codes are actually a subset of linear block codes. Yeah. So these cyclic codes, we can be able to derive them based on our knowledge of fields. Yeah. We are going to deal with Galois fields. Galois field just means finite fields. Yeah. Because there are fields which are not finite, but we are specifically dealing with finite fields, and we call them Galois fields. You can read the history of Galois. He's an interesting fellow. He died at 21, but he made a lot of difference in the area of error detection and correction. And I think what is sad is the way he died. I mean, it was a duel. He has been challenged by somebody to a sword fight, and that's how he ended. But he had done a lot by yeah. So he was called Evariste Galois. He was French. Yeah. Yes, Ogola, you have pressed your thing again, or is by mistake?
Yeah. I want just to ask, like, when you produce a syndrome which is not in the transpose of the parity check matrix, what is the implication of that? Because sometimes you can produce a syndrome which is not.
Or if you get a syndrome
Yeah.
which is not one of them,
Yeah. So little.
yeah, actually, it can happen if you have more than one error, because that only works with one bit error. If more than one error is one bit is in error, you will not get that. It's only when you have got when your error vector has only one bit. S1, yeah, I think that is the vector is has only one bit. Yeah, you get it. That is where be able to express the symbol. Right. This is the to establish where the error is. But if you have two errors, so then you're not going to get one of the error checks. Okay. So we are going to come across some polynomial set notation. So a lot of mentioning here. We write it like this: R, like this one is actually R adjoint X is an example. So for R, we are simply saying polynomials in. Okay, sometimes we use a variable, but is sometimes we like calling it indeterminate because it's just for determining the. I'm not getting indeterminate from determining, but it is used for determining the is an error. Well, is a position holder. Yeah. So for the zeros and ones. Yeah. So polynomials use variable x with real coefficient. So when you see r into bracket r adjoint x, yeah, that's what it means. Of course, it will mean different if you do rx. Yeah, we always do it like this because this is that would mean something different. So we are going to mainly work with z adjoint x, and in fact we'll be looking at what you call z star x, which is the same as the working with a finite field. The star wants to mean that it is finite. Yeah. So you're working with integers. We are going to see the different integers we can work with, but we will be more interested in the Galois field, where the integers you are dealing with is 0 and 1. Yeah. So R adjoint x, this will be an example of that. It means the coefficient are real numbers. Yeah. There is z x. This one, you can either say z2x or z star x, but I think this is one of the. So there's zx, z adjoint x. This is where the coefficients are integers. Yeah, 2, 3, 4, and this is z2x, where actually the integers are actually these are the Galois fields. These are Galois field 2. This is GF2. Yeah, but not all Galois field is GF2. You can have GF5. We are going to notice that it's only possible with prime numbers. So there is the Galois field has to be in prime numbers. They are not all integers, but just integers in certain in prime numbers. So we are going to see that. So this is how you represent. This means R adjoint X, Z adjoint X, Z2 adjoint X. So let's see the others. And how are these cyclic codes generated? We can look at this and see. Later we are going to deal with it. Why it is very easy to deal with the cyclic code generation. So if you have CX, which has got these bits or these coefficients, B0, B1, B2, B3, B4 to B5, where this represents just a bit. This is the bit which has X to the 0, is the bit of X to the 1. So the one with X to the 0, of course, we don't put X, because any number to the 0 is 1. So this X to the 0 is X to the 1, X to the power of 2, like that up to X to the power of 5. Where the coefficients are integers mode 2. That is the Z2. Yeah? Actually, this is how it looks like, integers mode 2. Yeah. So you have 0, 1. So whenever you talk of integers mode, whatever number you're talking about, it means that number is equivalent to 0. Yeah. So in this case, 2 is equivalent to 0. Yeah. And so if it's mode 2, it will not have 2. If it is mode 3, it will not have 3. Yeah. If it is mode 5, and why I'm saying that is because we normally use the prime numbers, mode prime numbers. So if it's a mode prime number, you can be able to create a finite set. Yeah. So the polynomials, these particular polynomials we are doing with here are in mode X to the 6 minus 1. So these are polynomial mode, another polynomial. Yeah. And you're going to see a lot of this where you have a polynomial mode, another polynomial. So what happens is X to the 6 minus 1 is definitely equal to 0, because we are saying when you have something mode, whatever number it is, and we normally say mode P, because for finite for finite sets, you would have, it has to be for finite sets, you have to have the mode, the P, whatever mode it is, has to be equivalent to 0. Yeah. And that's why you can see X to the 6 minus 1 is equal to 0. So we are saying X to the 6 is equal to 1. So you would have X to the 6. So whenever you get to X to the 6, we replace it with 1. So these polynomials mode X to the 6 minus 1, or in general, mode X to the n minus 1, will be able to generate a polynomial of length n, which represents a code word of length n. Yeah. So you can see this is, because this is mode X to the 6 minus 1, then it means that you can have 6 a polynomial with 6 elements. It has 6 coefficients, and these coefficients actually represent the bit 0 or 1. Yeah. So how do you get this this polynomial? If you multiply this polynomial with x, you're actually going to get a cyclic shift. Yeah, because if you multiply cx is this original polynomial. Yeah, if you multiply the cx, you're going to get x into b0 plus b1x plus b2x up to b5x to the 5, and therefore x cx will be equal to b0 x, b1x, b2x to the power of 3 up to b5x to the power 6. So you can see what you have actually done, because x to the power of 6 is 1. So this becomes b5 times 1. So this b5 now has come to the position of x to the 0. Yeah, which means it's a cyclic rotation, because this initially this was 1. Well, this means everything is 1. Yeah. So otherwise, the moment you have 0, well, let's say in this case, let's say b1 and b3 is equal to 0. I'm just saying that because what happens is whenever the coefficient is 0, we normally leave it out. So we are saying, let's assume this was b1 and b3 was 0. So this would be, if that was the case, it would mean this is 1. We are saying b1 and b3 is equal to 0. So it will be 0, 1, 0, 1. Oh, yeah, 1, 1. But what you are getting now will be, because you just simply moved this to this position. Remember, this x is a placeholder. So the moment you have x to the 0, it is coming to this position. And it's okay. Sometimes we use a convention where we start with x to the 5, x to the n minus 1. But you can also start with x to the 0 going to the x to the n minus 1. But if you use one convention, you stick with it. So for this case, we are using x. We are starting with x to the power of 0 and then going to the x to the power of n minus 1. Yeah. So once you move this one here, it means now whatever you're going to have will be the first one will be this one, because now this has become b0. You can see it has become b0 x. So it has moved its position to x to the power of 1. Yeah. So you end up getting a cyclic shift. So every time you multiply, you get a cyclic shift. That's why it is very easy to achieve a cyclic shift, because all you have to do is keep on multiplying the cx with x. Every time you multiply with x, so it is very, if you look at it, it's very easy to implement. Just multiply with that x, and then it keeps on shifting. Yeah. Anyway, we are going to see this clearly, but that is actually the definition of a cyclic code, and it's actually very easy to generate this code, and we are going to see with an example just now how that is achieved, even before we go to the science. of constructing these generator polynomials. So we are going to use a lot of modular arithmetic, and basically that's what we are using here. This is modular arithmetic, where we are seeing that x to the -1 is equivalent to 1. Actually, the keyword is not equivalent. If we have a better word, I keep on forgetting that word. Why do I keep on forgetting that word? I can't even remember that word. We don't use equivalent. This word means something else also. Equivalent is just one of them. But anyway, that's what it means. In modular arithmetic, I'm not using the correct word. So consider integers mod 7. 7 is a prime number. So integers mod 7 is one of the things that if we are going to see, you can be able to generate a finite set. Yeah? A finite set, not only a finite set, a set that meets certain axioms. Yeah? And later we are going to see what are the axioms a finite field must meet. Yeah. So consider integers mod 7, which we write sometimes we write z slash 7z or z7, where 7 is equivalent to 0. For now, we use that word equivalent, and here remember the correct word. There's a correct word that is used in modular arithmetic, but for now we can just use the equivalent. So 8 is 7 plus 1. So 8 is simply 1 mod 7. Yeah. 9 is 7 plus 2. So 9 is simply 2 mod 7. Z to Z or Z slash 2Z or Z2, which is actually GF2, yeah, is 2 is equivalent to 0. So 3 is equal to 1 mod 2. 5 is equal to 1 mod 2. Yeah. I think we have already dealt with this. Polynomials mod another polynomial. Like in that case, we were using x to the power of 6 minus 1 to generate the cyclic code. So this is an example. It's just z under in x slash x just means mod x to the power of 3 minus 1. So just a polynomial mod another polynomial, which is actually something we are going to work a lot with. But I thought of starting with the where we are dealing with just integers to understand the concept. But later, when you are generating codes, you'll be dealing with actually these polynomials mod other polynomials. Yeah. So in this case, whenever you see this mod, it means, and therefore x to the power of 3 is equivalent to 1. Yeah. So whenever you get x to the power of 3 is equal to 1, what it actually means is if you use these integers mod integers with the coefficient in x, I mean integers with the polynomials with integer coefficients, but mod this polynomial, it means you never have anything larger than with a higher degree than 2. because the moment it reaches the third degree, that becomes 1. So it will always be the highest degree of that polynomial will be x to the power of 2. Yeah. So like this, x to the power of 3 plus 2x minus 1. If you are dealing with mode x to the 3 minus 1, is simply equivalent to 2x, because this x to the 3 is equal to 1. So this will be 1 minus 1, so it just remains 2x. X to the 5 plus 1 is simply x to the power of 2, x to the power of 3, and we know this x to the power of 3 is 1, so this is simply equivalent to x to the power of 2 plus 1. And we are going to do a lot of this when you come to generating the BCH code. You are going to find that this arithmetic is very important. Yeah. Yeah. So to make cyclic codes, oh yeah. So we are going to see that you can be able to generate cyclic linear codes. Yeah, to make cyclic codes, you simply keep on multiplying by x. If you multiply this by x, you get xcx. If you multiply again with x, it becomes x to the power of 2cx, and so on and so on. And this creates a cyclic code. And to make it linear, what we have to do is just use cx plus. So you just add this. Adding this actually creates cyclic linear codes. Because what we are saying is to create a linear code, it means you are adding code words. You're adding code words to create another code word. Remember, that's what the definition of a linear code is, where adding 2 code words generates another code word. Yeah. So this is one of the code word. You have generated another code word. You have generated another code word by just doing cyclic shifts. But now you can create cyclic and linear by now adding those code words. You see, like you add cx plus xcx plus, you don't have to add all of them. You can just actually add this and this, and you get a code word. You can add this and this, you get a code word. You can add this and this and get a code word. Yeah. So a valid code word can be generated like this. Like this would be a valid code word. Yeah. Yeah. Oh, you're saying it can be generated by this. Well, we are going to see here we just can be generated by this, but I think now we'll see later how to generate this. So we are saying this can be a valid code word, a valid generator, but you see how you decide on the valid generator. The valid code word generator, or another generator polynomial, needs to have certain properties. Yeah, and we are going to see that once we begin talking about minimal polynomials, prime polynomials. So, like here, we have generated a cyclic linear code. We are using polynomials in mode 2, yeah, with the coefficients in mode 2, mode another polynomial. Yeah. So this is polynomial mode another polynomial, but this polynomial has got coefficients in mode 2. Yeah. So 2 is equal to 0. So it actually means where you're dealing with binary. And so generally we'll be dealing with this Z2X, what we also call GF2. the lower field 2. So in this case, we are saying we have code words which are 000, and in this case, we have identified that this can be used to generate. So for now, we are saying this can be used to generate this code. But later we are going to see how do you arrive at this. Yeah. Because to arrive at this, it means you cannot break down this. This is a prime polynomial. Yeah. Because you're going to deal with the prime numbers. So when you deal with this, we actually call them primitive. We are going to see that this is a primitive polynomial. Yeah. So we are going to see just now, when you're dealing with prime numbers, why prime numbers are important when it comes to generating fields. Yeah. So in this case, we're using this as a GX, and we are saying if you have got your code word, your message bits, these are your message bits. In this case, we are talking about 6-bit code word. So the message bits are 000, and the error checking bits. There are 3 bits and the error checking bits. For this scenario, if you have z to the 6, this is z to the 6 minus 1. Yeah, not z. You can correct that in your notes. So z to the 6 minus 1. So if you are doing with this one, then it means it's a 6-bit, and the message bits are 3. So the error checking bits are 3. And we are saying we can get the first code word, which is the 0 code word, by simply multiplying the 0, because this is 0. Yeah, this is 0, and then you see how we have done this. And we are calling this. Sorry. It's because of the convention we have used. We are starting with the lowest, x to the power of 0, as opposed to the highest. That's why if you look at this, it will mix you up. Later we are going to deal with why you start with the highest power or the highest degree. But we are just starting with the lowest degree. But it demonstrates the same concept. So we have used this as a polynomial. This is a GX. So we are saying if you multiply this with the GX, which this is 0, you're going to get the 0 code word. The next one, we are multiplying the same GX with 1, and we are calling this 1 simply because we are starting with we are using this convention. Don't be confused, because if you are using the other convention, this 1 will be here. Yeah, but now 1 is here because we are using this, where we start with the lowest degree going to the highest degree. Yeah. So you multiply that, of course, you're just going to get GX. You see, the GX itself is one of the polynomials. And now you can see the others. These 3 are simply a cyclic shift. You can see this one is shifted. These 3 are just cyclic shift because you are just multiplying with x, and again multiplying this with x. So these 3 are just a cyclic shift of each other. Yeah. If you shift, you get back to this one. So up to here, you can get through just cyclic shifts. That is x and x squared. And now with here we are using the linear. So what we are doing is we are adding gx and xgx. Yeah, you can see these are 2 this is gx. 1 times gx is gx plus xgx. So we're adding this one and this one to get this one. Yeah. Then this one, we are adding xgx and x squared gx. So we're adding this one and this one. This one, we are adding gx and x to the power of 2 gx. So we're adding this one and this one. And the last one, we're adding all of them to get this code word. So there's a linear, a cyclic, and a linear code word. Yeah. So you can get it, and of course, what happens is each these are the ones which are cyclic. It's both linear and cyclic. Yeah. It doesn't mean you get everything by cyclic. It means part of it is, some of it is cyclic and some of it is linear. So let's look at what you call algebraic structures. Yeah. So on an empty set S is called an algebraic structure with respect to an operation. So whenever you define an algebraic structure, you have to define it with respect to an operation, and we use the star to refer to any operation. So star is a general, it just means that this can be addition, multiplication. Yeah. So we use this star operation star if A star B is belongs to S. I don't know what that calls a star or asterisk, but I think it's more just call it star. Belongs to S for every A, B belongs to S. What we are saying is that if you have a set and when you carry out an operation, whatever you get is still within that set, then we can say that is a structure with respect to that operation. Yeah. So algebraic structures include groups, rings, and fields. But you see, I started with groups, but our main interest is the fields, because it's the fields that give us that ability to construct code words. Yeah. So a group is a set on which, so of course the one of the main structures we are going to do with is groups, rings, and fields. So what is a group? A group is a set G on which the operation addition, is defined and satisfies certain basic rules known as group axioms. We expect a group to be able to satisfy those axioms. Remember, axioms are things we know, but we don't have to prove. Yeah, they are different from theorems. Yeah, so these are just group axioms. So one is associativity, that is A plus B plus C is equal to A plus B plus C. You are saying in this algebraic structure called a group, yeah, you find that if you take any three numbers, any three members of that group, you can actually do this. There is associativity. Yeah. There is an identity element E belonging to G, belonging to the group, such that E plus G and G plus E is equal to G for all G belongs to G. What you are saying, what constitutes a group must have that identity that you add. So that would mean, I think real numbers would include this, because real numbers would include G, 0. You see, in this case, E has to be 0. So it means a group has to include 0. If that number you add, it is still going to be G. Yeah? For all G belongs to G. Yeah. Then there's an inverse. For every E belonging to G, there exists G inverse. Sorry. For every G, this is a problem. For every G belonging to G, there exists G inverse belonging to G, such that G plus G minus, G to the G inverse is equal to G inverse plus G, and is equal to E. Some identity. Yeah. So we are going to see, I think this is the identity we are talking about. So we are going to see that this would be, of course, if it is this an additive universe, we are going to see also there is a multiplicative universe, but this is an additive universe. Yeah. For example, I think the set of real numbers would have this property, but the set of positive integers will not have this property. There's no other number you can add to another number in that set to get a 0. If they are the positive integers, 1, 2 to infinity, there is no way you can add two numbers which are greater than 0 to get a number which is equal to 0. So, for example, it means that will not constitute a group. Yeah, because that will not happen. An example of group is Z, the set of integers with respect to addition. But that is Z, group of integers, not positive integers. Yeah. If you remember you add positive integers, it ceases to be a group. Yeah. So that is yeah, we have 3 minutes. So I was wondering whether we can use those 3 minutes so that and I was having a proposal. I don't know whether that proposal is agreeable with you. This 1 hour, is it possible to combine this hour with the 2 hours? And we start our class at 7 online, 7 to around 10 or even 9:30, 7, 8, 9, even 9:30. What? Except this coming one, because tomorrow we said we are meeting physically. So I'm thinking, can that be a good proposal? Who thinks that's a good proposal? So we don't meet for the 1 hour. We meet for 2.5 to 3 hours on Tuesday. We start at 7. Would anybody have a problem of starting at 7? Because me, I wouldn't.
I think it's a good proposal.
is a good proposal. So from next week, we will meet on Tuesday. We will be meeting. No, we will meet on Wednesday. We will be meeting on Thursday from 7. If everybody is agreeable,
I think we should first let the class to vote on that because 7 is early, I think, for others. So maybe we should let people vote first, then we can tell you.
we should look. We should or you want to consult before you make a decision?
Yeah.
Okay, so you can consult, then you can give your class rep your final decision. But I was just proposing, of course, we can start 7 and go to 11, but I was assuming probably you have got something at 11. Yeah, that's why, no, 7, 8, 9, 10. 7? No, sorry, 8 to 9. Yeah, we can start at 8 and go to 11. But again, I'm not sure whether you have something at 11. So discuss as a class and agree, and then we can look at that with your class rep. So tomorrow we'll meet online at 8 o'clock. I think we'll get a room so that we can go through some examples.